Okay. Today we try to use a Skyrim platform to for the class, but our experience was not good. So I decided to come back to the Adobe Connect for the rest of the course. Uh, from the next week, I will upload some exams for you. Mm, Each exam consists of the context of one chapter. The exam in the next week is related to the content of chapter 1 of the book. And after that, in the second week to next week's, we have an exam from chapter 2, and in uh, next 2 weeks we will have another exam from chapter 3. So in the next Tuesday we will have an exam. Please read the content of chapter 1 for the next week. Also, today we will finish the content of chapter 3, inshallah. And after that, I will record a video of Veka, and I will show you how we can use Veka for pre-processing. However, you can find more videos in the internet too. After that, I will put the new assignment on the LMS. In the LMS, the new assignment is related to pre-processing, and I will ask you to do some pre-processing steps using Weka in the dataset, in adult dataset. You have 2 weeks time to do the second assignment. So next week we will have an exam from the next week, and also I will put a new assignment in the LMS for you. Okay. Have you any question from the past lectures? If yes, please ask me. Please write in the chat room. If you have any question from the past lectures, please write in the chat room. Okay. In the past lecture, we talked about data transferring, and finally, at the end of that lecture, we talked about data discretization, and we said that there are several methods for discretization. One of them is binning. And as I said, binning is near and is close to the histogram, to creating a histogram plot. Binning is divided into two different to different section, to different method. The first method of binning is creating beans with equal width, and the second method is creating beans with equal depths. If we use equal width strategy for creating beans, it means that uh, I should sort the data ascending and then ascending or descending. Uh, it's not important. I should first the data. I should firstly I should sort the data, and then I should divide those data into some predefined uh, partitions. Each partition has an equal width. For example, let's suppose that I have some data. The lowest bound of data is A, and the highest bound or highest value is B. And I'm deciding to create n different partition or beans. The width of each beans can be calculated using this formula. W is equal to B minus A divided by N. B is the highest value in my data set, and in my set of values related to one specific attribute. B is the highest value in that set, and A is the lowest value in that set. And N is number of beans. So simply, I can divide the range into N and find the width of each beans. This method is simple and straightforward, but for the cases that we have outliers in data sets, or for the cases that the data is skewed into one side, left skewed or right skewed, this strategy has low performance. In equal depths or equal frequency strategy, we make some beans and then we put data in that beans such that each bean have equal number of items. Each bean must have approximately, or not equally, approximately must have similar number of samples. In this case, one bean may have a wider width and one bean may have a short width. Okay. This strategy has a good scale, and overall it has a better performance than equal width. Why? Let me show you why. For example, let's suppose I have let's suppose that I have data in this with this distribution, okay, and in equal widths I define bins with equal widths, something like this. Here, in this case, you can see that we have, for example, 6 bins. 1, 2, 3, 4, 5, and 6. We have different 5 or 6 bins. Okay, you can see that in this case, you can see that the first and the last beans here, the first and the last beans has the minimum number of items. Comparing with, for example, beans number 3 and number 4. Comparing to them, for example, the fifth bin is empty. Why? Because the data is skewed and is the distribution of data is skewed. The data is scattered in a small region. But when we are talking about the equal depths, equal depths that means that I should create some bins with equal number of items. For example, in this example here, in this example, we can see the width of the first and the last. The width of the first and the last bins are wider than the width of, for example, bin number 3 or bin number 4. Why? Because we increase the width of these bins to put more items in their range. So using equal widths, making some changes in our strategies. Okay. Now, suppose that I have 12 different items, data items. Yes, Muhammad Hassan. Okay. Suppose that we have a set of values, different values 4, 8, 9, 15, 21, 21, 24, 25, 26, 28, 29, and 34. Okay. And my strategy is equal depth or equal frequency beans. And I'm looking for 3 beans. So each bean must have 4 different items. Each bean must have 4 different items. The first bin consists of 4, 8, 9, and 15. The second bin consists of 21, 21, 24, and 25. And the third bin consists of 26, 28, 29, and 34. Okay. We simply divide the items in 3 different categories. Number of items in each category or each bin or each group is equal. Okay. After making the bins, as we talked in the past, maybe my results affected by noise or outliers. So simply I can apply smoothing techniques on data of each bin. For example, one technique of smoothing is to find the mean value of data in each bin and then replacing all values in that bin with the mean value. For example, in our case, the bin 1 consists of 4, 8, 9, and 15, and the mean value of these items, 4, 8, 9, and 15, is 9. So I can replace 4 values with 9. I can repeat the same strategy for bin 2 and the third bin consists of 29, 29, 29, and 29. Another strategy is binning the boundaries. For example, in our case, the first bin consists of the lowest value of 4 and the highest value of 15. So I can smooth the result using this 4, 4, 4, and 15. The second one, the lowest value is 21st, and the 21, 21, 21, 25, and the third being 26, 26, 26. Here. Okay, in this example here, you can see 2 okay. So in the boundary, in smoothing using boundaries, we replace all items with the lowest one. Just the last item is replaced with the highest value in that bin. Maybe someone asks me, okay, which of these smoothing techniques is better? If you ask me, I will say I don't know. Why? The answer is simple. I should do everything according to my goal in data mining. So I cannot say that, for example, smoothing using means is better than smoothing using boundaries. I cannot say. It depends to the situations. Okay, see this example here. We have some data objects scattered in a 2D space with 4 different colors, like this. Okay. In the top right, you can see the results for binning using equal width. You can see that the data are ranged between 0 to 20, and we are looking for 4 different bins. So simply we divide 20 by 4 and the result is 5. You can see here we have 4 different bins with equal width. Look at this figure. Here you can see that the border line, the dashed line in black, are borderline between 2 adjacent bins. You can see, for example, the borderline is drawn such that half of the blue objects are in the past in the left side, and the rest of them are placed in the right side. We can see similar effects for yellow and red. This result shows that equal width binning is affected by the has low performance to discretize these data. The third image, the third plot, is related to the strategy of equal frequency or equal width, equal depths. Here you can see some bins are wider and some of them are smaller. In the bottom left. And finally, we apply a k-means clustering techniques to our data to divide those data into some bins. Wow, that is interesting. K-means is just a simple clustering techniques, but the result is interesting. K-means could divide the data into very clear bins. You can see K-means works well. However, we should note that one algorithm may act good, very good, and sometimes okay. We'll talk about clusterings in the future in I think chapter 10, I think. So don't be care about them, but just here we should be clear that if we use a more intelligent item, right now we're just talking about these techniques, talking about binnings and something like that. There are two other options or two other methods for discretization and finding the intervals. One of them is using classification techniques, especially decision tree. Decision tree is a system helping to make a decision. In the future, we will talk about classification and its techniques. But shortly, we can say that classification is a supervised technique. It's a top-down with recursive splitting. And when someone the detail of classification will be mentioned in the near future in chapter 8. Decision tree is a tree that makes some decisions. It helps to make some decisions using the structure tree to making decisions about different fields and areas. One more method for discretization is analyzing in correlation analysis, for example, something like Q2. Still, we are using supervised learning, but this strategy is a bottom-up strategy. In classification, we are the correlation analysis is a bottom-up merging system. This means that during the binning process, we should merge two adjacent for example, you can find two different items or two different beans, two different neighbor beans, and simply we test them, and if they have similar distribution and similar items, then by merging those beans, we can reduce number of beans easily. We merge smaller beans and making a bigger one. This is a bottom-up merging strategy for to use correlation analysis. Okay. One more important thing here is the concept of hierarchy. When we are talking about hierarchy generation, it means that create some trees. And then according to the worth of data, put everything for example, think about address. Okay. In the address, we have different levels of information. In the lowest level, the hierarchy can be, I can approximate a hierarchy with a tree. Okay. In the lowest level of the hierarchy, think about a hierarchy for address. In the lowest level of the hierarchy, we have street. In the upper level, we can think about the city, name of city, and in the top level, we have city. In the one more type level, after that, in the upper level, city, state, country, region. We can have different items here in different levels. But look at this. Look at this. For example, one of you, for example, Ahmed Zahra. Ahmed is a man from a city in Iraq. And all of you are from different cities. In an upper level in the hierarchy of address, We have, for example, a state. All of you are standing in some different states. In an upper one, after state, in the upper level, we have Iraq as country. In the upper level, Iraq is stand in the Middle East, and in an upper level, the Middle East is standing in Asia. So I can say that instead of saying different items based on my conditions, I can replace the data in each record using those data in different levels. For example, here, street, city, state, and country. There are 4 different options. Each of them has standing in a level, in a specific level. And when you want to talk about the values, it depends on the level that you select. For example, Urbana campaign and Chicago. All of these cities are in the Illinois state. So instead of saying names of those cities, I can say, for example, this is for Illinois. This is an address in Illinois. So when we are using the hierarchy, we can make the data easier than before. And also, I can hide some information. For example, let's suppose I have a data set from patient's information. Okay, and in that data set, we have name, family, and address of each patient. So if I have a hierarchy for address, simply I can go through that hierarchy, and instead of saying, for example, the real address of the user, simply I, for example, instead of saying, okay, I'm in the street X, in the city of Y, and in the state Z. In such case, to keep the privacy of data, I can simply say that, okay, this is an Iraqi patient, for example, instead of saying name of street and then saying, for example, suppose that someone is in Karbala, in one of the streets. For example, Zainab Street in the Karbala. Okay. Instead of saying something like that, I can say that this patient is from Karbala. So I keep him or her privacy just by going through this hierarchy, going up. And one more interesting specification for hierarchy is that when we are going through this hierarchy, the number of distinct values related to each level will change fastly. For example, in the address, if I'm talking about the street, for the street in an example, we have more than 600,000 distinct values for name of a street or something like that. But if we are going toward, we can see for the country, we have only 15 distinct value. For a street, we have more than 600,000 value, but for country, we have only 15 distinct value, different values. So just by going through the hierarchy and replacing the data, I can remove the complexity of data and I can make it simpler. And maybe I can remove some private information, keeping the privacy of the users. Okay, this was the last part of chapter 3. Here in chapter 3, we learned that before applying data mining techniques, we should to improve the quality of data. So we talk about data quality and we say that, okay, the data, there are 4 different major tasks for pre-processing: data cleaning, data integration, data reduction, and data transformation and discretization. We talked about them and we show we saw some example too. But as we said in the future, having a simple data having simple data can make our data mining work easier than before. So we are applying pre-processing steps to make our data simpler than before. Just this, to make the data simpler than before. by removing irrelevant data, by removing noisy data, by removing outliers, by integrating data, by compressing, by reducing features, reducing maybe sometimes reducing total number of information, and so on. All of these 4 steps only, all of these are only should be done before applying the data mining. And which of them can be used is depends to our goal in data mining. In for some algorithms in data mining, maybe I should keep all data. For some others, maybe I should remove the data. This is the end of chapter 3. Is there any question? Okay. I will record a video for you